So when we do the actual program relocation, there are two types of relocation. One is called a static relocation, and then one is called a dynamic relocation. So now what's the difference between these two? Let's see. Let's see. Okay. So here is an example. Okay. Now on the left, this is actually, you can interpret this as a source code. Okay. It's just like a Java code, right? So you declare an integer I, int I, and then you assign a value I equals, I don't know, maybe 100, maybe 200. I assign a value. Okay. And then down the road, there's another statement that says I call a function, I call a method. Okay. I call a method. So this is a source code. We know that the computer cannot read the source code. You have to convert this into a machine code and eventually load the machine code, which is actually a whole bunch of instructions, and then load the instruction into the computer system. So, so then we're going to compile the code to convert into the code the machine can understand. So then we're going to convert this statement, like assignment, into something like similar to the assembly language or machine code. It's called a store. Okay, so that's basically you're going to store the value into memory address 20. So this is memory address. Okay. Now at this moment, and then you're going to actually put the actual number in the memory address. If I say I equals 100, for example, and then in the memory address 20, I'm going to store the value 100 in there. Okay. Now, this is the memory address. So that means store into memory address 20. Okay. So the 20 actually stores the value 100. Now, just keep that in mind. This 20 is actually a logical address because this is, we are still talking about the whole program in terms in terms of a whole bunch of instruction. So the program actually starts from logic address 0. Okay. So 20 is the logic address of, you know, so this logic address stores the value 100. Okay. So eventually this, you're going to store the 100 into the appropriate location. And then for the function call, I'm going to actually write the instruction called call f. Okay. So the call is some kind of command in an assembly language or machine code that you're going to actually say, I'm going to call f. Okay. So once you compile this code, and this is called object code. Okay. S is a source code. Okay. So that's called object code. Now, can I run the object code? The answer is no, because the object code is still a logical, stored in a logical memory address. So it's not really a physical address. It's not even loaded into the physical memory yet. Okay. And then when I actually try, before I load it into the physical memory, I need to actually link the object code into some other modules or library or something else. So some of the code doesn't need to be linked to anything, because if the code is so simple, but some of the code, like if I have to call the memory functions, I have to do the link. Okay. When I do the link, then I need to actually say here, I'm going to call the method or function f, right? So after link, the f could be a function defined in the library, but during the link time, I have to, make sure this function the implementation of the function, the actual function, will be loaded into the loader module. Okay. So then I'm going to link the function to this object module. So this is the object module. Okay. And this is actually the actual implementation for the function, the blue color. So then depend on where I'm going to put the function in the, so I can reorganize the logical memory. So the logical memory actually, so the whole load module is enlarged. It's bigger than the object module because I just actually combine these, you know, I actually combine the function implementation with the object module and then link them together, right? So the loader must adjust all so the logical address has to be adjusted because the module size is bigger. So here's how I adjusted the logical address. So I'm going to put the function implementation at the beginning. So the function actually starts from the logical address 0 instead of this object module. So the object module starts from 100. So that means the instruction, the first instruction in this object module will be loaded into 100, logic address 100. It used to be 0, but now it's 100. So every instruction over here will have to be shifted by 100, right? So the logic address 20 in the object module will be shifted to 120 because the first actually instruction actually shifted from 0 to 100. So 20 will be shifted to 120. Okay. Now when I actually say store to the logic address 20, so I have to change the value and replace the store 20 to 120. Okay. Now when I say over here in the object module, I say call a function, and then because I have linked the function and put the function in the logic address space. So the function is actually start from logic address 0. So when I say call f, I actually going to call 0, which is the beginning of the logic address for this function. So that's the load module. And then the load module is the module so that you can load into the physical memory. Okay. So that's so you have to put the load module into the physical memory. Now when you load it into the physical memory, and there going to be one more program relocation. So you have one program relocation here, you have a relocation here, and then you have a relocation here. That's supposed to be the final relocation. And then when I load the whole load module into the physical memory, then I decide to load into the physical memory 1000. Why you want to load into the 1000? I don't know. It depends on which memory space is available, right? So every time when you actually, today when I load this load module into the memory and I find out the memory space at 1000 and after is free, so I can load it into the 1000. But next time when I load it, when memory space 1000 is not free, so I have to find another location. So this relocation, so every time when I load the load memory, it's not always loaded into the same physical memory location. It depends on which part of physical memory location is free. So this time I'm going to load it into the 1000. So then the load module, the logical address 0 going to be mapped to 1000. So everything else going to shift 1000, right? So 100 becomes 1010, 100 becomes 1100. and 120 becomes 1120. Okay, so you have to do the corresponding mapping. Okay, when you say store 120, now I have to store into 1120. And then when I call 0, which is the location of the function f, and then the physical location of function f is mapped to 1000. So when I have to change this logical address 0 to physical address 100. And then this is actually in the physical memory. This 1000 is actually the physical memory address. And this physical address is actually loaded with the function f. Okay. And this store the memory address, that's a physical memory address. So this physical memory address actually stores the value 100. Okay. So from the beginning, from the source code, compile into the object code and then link into the load module, uh, and then load into the memory, you have to actually relocate the program a couple of times. Okay. Now this is called statical relocation. Why it's called statical? Because when I load everything into the computer memory, everything is decided. Okay. Everything is loaded. Okay. So when we say statical, you know, basically we say, you know, after the compile, after the after you compile the code, and then so everything is actually loaded into the memory. Now, dynamic reloading is kind of different. Okay. So the difference between static relocation and the dynamic relocation is that once you got the loader module, once you load the code into the physical memory, okay, there's nothing wrong with this, right? You just load everything into the physical memory, and the 0 maps to 1000, and the 100 maps to 1100, and 120 maps to 1120. Okay. However, in the actual code, so I don't have to change this. Okay, don't have to change this because the time when I actually change this value is when I try to execute this statement. And then when I execute the statement and I find out, oh, this is still the logical memory address. So it's not a physical memory address, because if this is a physical, then it's going to be somewhere before this 1000, right? So 120 probably going to be over here before this 1000. But we know that because this loading is dynamic loading, so that means once we load the program into the physical memory, some of the memory addresses are still logical. Okay. Now in this case, we don't even actually we still actually say 0. Now when you actually execute the instruction, execute this statement, and then we're going to start to actually convert. We start to convert this logical address into the physical address. Okay. Now how we're going to do the conversion? That's something we're going to talk about next. Okay. So the idea is, because once the program is loaded into the physical memory and the start physical address 1000, this is very special, and many times we call this relocation variable. And then we can actually load this value into a computer CPU register, and this is going to be loaded into something called a relocation register. So if we decide to use the dynamic relocation, and then we can actually copy the first physical memory address for the whole module into relocation register. And then relocation register going to be used to convert each of the logical address into the physical address. Remember that the physical address actually can be easily calculated by adding the relocation value in the relocation register plus the logical address, right? So this is actually very simple math. So for example, if the logical address is 120, now the physical address is going to be 120 plus the relocation register, which is 1000. So 120 plus 1000, that's 1120. So, but this calculation is basically done in the fly while the program is running, not like this static relocation. It's already done when you actually load the whole program into the computer memory, and then every actually logical address has been converted into the physical address. But the dynamic relocation is not. You're not going to actually convert every actually logic address into the physical address, but this is actually done only when you execute the program. So that's called a dynamic loading. Okay. So in the dynamic relocation, a relocation register is actually used. The relocation register contains the physical starting address of the program or the program component in the memory. So in the previous example, the physical starting address is 1000, right? That's the physical starting address. Okay. So this address is going to be stored in the relocation register. Okay. Now, there are two different type of dynamic relocation. One is just to actually use only one relocation register. So in this case, because most of the program consists of three main components: the code, the program part, okay, the code, okay, and also the statical data. So whatever the values you're going to use, and also the dynamic data. Dynamic data is basically generated. It's actually calculated during the execution of the program. So code and the statical data can be stored during the program load. But dynamic data is not, because dynamic data, before you start to execute the program, the dynamic data may not even be there, right? So it will be actually computed during the execution of the program. So dynamic data are typically stored in another location called a stack. The stack is a fit memory location that they use to store a temporary data. Okay. So there are two actually dynamic relocation. One is you treat all three components as one unit and use only one dynamic relocation register. The other approach is you use three relocation register. One for the code, the program, one for the statical data, and one for the dynamic data. Okay. And each, you know, so when you have a program, that's the code, that's a place for the data, statical data, and that's for the dynamic um, data. That's a stack. Okay. So now static data actually start from memory address 20. Physical code start from memory address 100, and dynamic data start from memory address 200. So then you're gonna have three different relocation register The first relocation register will store the value 20. The second one store the value 100. And third one store the value 200. Now, depend on which data you want to access. If you want to access a particular instruction in the code, then you're going to use this relocation register. If you're actually going to access the static data, then you're going to use this relocation register. And if you want to actually try to find a particular data, a dynamic data, the temporary data just generated actually during the execution, then you're going to use this 200 as a relocation register. Okay. So these are two different type of dynamic relocation. Okay. Now here we treat the dynamic as the whole loader module as just one piece. So we only use one relocation register. Okay. So now how are you going to do this? Let's take a look. Okay. So this is actually a diagram which basically shows how the CPU going to actually perform the dynamic relocation. Okay. Now forget about the limit register. Limit register basically for each program, they are actually, besides the relocation register, so in this particular case, the relocation register is 1000, right? Now there's another limit register for the program. It's called a limit register. Limit register basically tells you the basically size of the program. So if the program starts from 1000 and it ends at 29.99, okay, 29.99. So what is the limit register? Limit register is actually 29.99 minus 1000. It's a 199, 1999. Because you start from 1000, you end at 2000. So the limit register basically tells you the size of the program. Size of the module. Okay. So this is the limit. So basically, once a logical address is actually introduced, so here, if it's a logical address, and then for this particular example, if I say, okay, store to 120, okay, I know 120 is logical address, so I just put the 120 here. Okay, the CPU actually checked the 120 and check with the limit register, say, well, 120 is within this limit 100 limited actual register. So that means this is a legitimate address, right? Why? Because if it's 1999, so if I load into the physical memory from starting from 1000 to 2999, and then that means in the logic address scheme, this is actually 1999, right? Because after you load, it was 1000 shift. So 0 becomes 1000, but 1999 becomes 2999. So that's why when I compare 120 with the limit register basically tells you the last actually logic memory address for the program. So that's the size of the program. Okay. So when you compare this and I say, oh, 120 is less than 1999, so that means it's a legitimate address. Okay. If the logic address you request is like a 25,000, 25,000 compared with 1999, 25,000 is greater than 1999. And then we're going to say, no, this is actually address error. Why? Because 2999 is actually beyond this range. Okay. So the legitimate logical address is actually between 0 and 1999. So 120 is less than 1999. That's okay. Okay. So in this case, the answer is yes. It is less than 1999. So I'm going to go over here. And then 120 going to actually plus the relocation register, which is 1000. So then the physical address is going to be 1000 plus 120. So it's 1120. And then you're going to actually refer to the physical memory address 1120. So in this case, you're going to actually go over here and refer to the physical memory address 120. And then you got the value 100. Okay. So this is actually the program relocation. It's pretty straightforward. So for every actually logic address, you're going to compare with limited address, limited register, make sure it's within the range of the program. And then you're going to add the relocation register, and that's the physical memory address. Very straightforward, right? Okay. When you call 0, and then you're going to say 0, and 0 is less than register, limited register. So go over here, and the 0 plus 1000, and that's 1000. So then you're going to call 0, and you're going to actually call 1000, right? That's the location for the function in the physical memory. Okay. Any questions? So this is another, this is a similar example. So the program is actually loaded into a physical memory starting from 500. So the 500 are going to be loaded into the relocation register, right? And then for every address, like 80, so 80 going to be actually added with 500. So the physical address for 80 going to be 580. Okay. You know what I mean? If the physical actually if the program is loaded into a different physical memory, if the physical memory starts from 100 instead of 500, and then the relocation local logical address going to be added to a different relocation register value. And so 80 going to be added by 100, and it becomes 180 instead of 580. So this is basically how you're going to decide what is the physical address for each of the logical address. Now here, if you treat three components, the code, the statical data, okay, and dynamic data as a separate one. So now you're going to have three different relocation register. So then when you actually say, oh, you know, you want to call this address 0, then I'm going to actually, the 0 going to be plus the 500, and this is actually 500. So that's the beginning of the code. And when I load the data, which is actually the statical data, and then so I'm going to go over here and add the relocation register for the statical data component, and then the actual data. So the load the data 220 going to becomes 220. Okay. Now this is like dynamic data, and then if it's actually going to be relocation register going to be 800. So this is a little bit more complicated, but you use actually 3 relocation register because depend on which logical address space you're going to try to access. If you try to access the logical space for the code, or if you try to access the logical space for the statical data, or the logical you know, the logical address for dynamic data, then you have to add the different relocation register. Okay. So that's basically the program relocation. Okay. From the very beginning, your source code compiled to the object code, and from object code, you're going to link the library code and the other module. You becomes a load module, and the load module and the loaded into the physical memory, and you're going to actually experience couple of program relocation. Okay. Now, the next topic we're going to talk about is the space management for the memory. Okay. So when program is loaded into the memory, so that memory space is used. And when another program wants to be loaded into the memory, and the operating system need to check where I can find a free space in the memory. Okay. And then load it into that free space. That's the another important task for the operating system memory management. Okay. So the operating system keep track of all free space, and we call it whole. Okay. So you can use various different technique like linked list uh, to find the whole and find a space that is loaded. Okay. Operating system also must coalesce any neighboring holes resulting from the removal of the programs from the memory to prevent memory from becoming a fragmented collection of the increasingly small hole. So here's example. If I have this is a memory, right? Okay. So now this space is loaded with a program, and then now initially you can always say, okay, when I load the program, load one program here. Okay. So starting from memory to 100. And then when I load the second program, if another program wants to be executed, so I need to load the second program into the physical memory. And then I can, ideally, I should actually load the second one, start from 101, right? And then over here. But that's not likely the case. One reason is, what's the reason why I cannot load another program right after the first program? Why? Because when you think about this, the actual program execution, during the execution of the program, you're going to create some temporary variable, right? And calculate some temporary data. And these temporary data are going to be stored in the dynamical data location and like a stack. So the program initially, when the program is loaded into computer memory, as you start to actually execute the program probably going to request for more memory space. So the program is loaded into computer memory from 0 to 100, but as the program is executing, it will grow. So you have to leave some room. Okay, say here I'm not going to use that space. I reserved for the program one, because as the program one is actually, when we start to execute the program one, the program one may need more actual memory space. So when I load the second program, I may actually start the second program from here. And this is actually a hole, right? And the hole is actually sometimes bigger, sometimes smaller. You never know. And then another program starts from here. And that's another hole. Okay. Or you can actually start from here. And then you can actually probably put a stack of this program in another place. Okay. So, and then when one of the program actually complete a job, like this program finish a job, it's gonna actually remove its, the operating system gonna remove this program, this particular program from the memory, right? So once the program finish the job, and then what I'm gonna do is I'm gonna remove this one. Okay. So free of the memory space. If this one complete, okay, I'm gonna remove it. Okay. So I can also remove it. So you can imagine that once the program is loaded into the memory, and that the operating system find a memory location and load the program. And then when the program finished the job, the operating system is going to remove the program from the memory and free up the space. So it's kind of like a dynamic operations. So some programs actually added into the memory, some program leave the memory, some another program added into the memory, another program leave the memory, and after for a while, you will probably imagine that the computer memory is just like this. Okay, so you may actually have, a whole bunch of like a whole bunch of programs loaded, and then there's a holes in between, right? These are the hole. Okay, and these are called block that currently used by at least one of the program. Okay, these are the blocks. Okay, and these are the holes. So now in the computer actually memory management, there's a couple of different actually strategies to load the next program. Okay, so if you have a program, distributed like this, okay, so these are, let me actually erase all this. So after you execute all the programs, you use the actual computer system, and then after for a while, the memory gonna be like this. So you have a whole bunch of programs loading into memory, and you have a whole bunch of holes scattered all over the memory location. Now, if a program is actually is created and wants to be added into the memory, what are you going to do? So you're probably going to search the memory location and find a hole, right? Then you can fit the program into the hole, right? You can fit that into the hole. Now, there are a couple of different strategies, okay? One is called first fit. And then there's a next fit and the best fit, worst fit. Okay. So what is the first fit? So if program is created and want to be loaded into the memory. So what I'm gonna do is I'm gonna start from the beginning and start to search the hole. I check the first hole and compare the size of the hole with the program, and I find out this hole is not big enough for the program. So I skip and I search the next hole and I compare the size of the hole with the program, and I find out this hole is big enough for the program. And then I fit the program into the hole. And that's called the first fit. First fit means I start the search from the beginning of the computer memory for any hole that's big enough for the program. Okay. Once I find the hole that's big enough for the program, I put the program in, I load the program into the hole. That's it. Okay. That's the first fit. A next fit is very similar to the first fit, except that once you actually fit the program into the hole, and then I just mark this location and I say if there's another, then I just put the program in here and mark this location. Sorry, not this one. Okay, so when the next program is requesting for computer memory, and then my search is going to start from here and search for all the holes until to the end of the memory location. That's called the next fit. Okay, and the next one is called the best fit, and the best fit is just like basically you're going to search the entire list of the hole and choose the smallest hole large enough to accommodate the request. So suppose in this case, I'm going to continue the memory, right? Here, here. Okay. And then if I have a next program coming, so the best fit basically start the search for the hole, and I check the first hole. First hole is smaller than the program size, so I skip. And the second hole, it's still small compared with this one. You cannot fit this program into the hole. Okay. And then I search this hole. Well, that's big enough. Good. If it's a first fit, then I'm gonna put this program into the hole, right? But for the best fit, I just mark this hole, say, okay, this is a potential candidate. And then I continue the search and find the next hole. And next hole is also big enough. Okay, and I find the next hole is also big enough. So in total, I find 3 holes that are big enough for the program. Now the best fit basically gonna choose the smallest hole in this 3 and then put the program into the hole. So in this case, this is the biggest one, so I skip. And next one, compare this one, and this is the smallest hole that's big enough to accommodate this program. So I'm gonna put this one here. It's almost like a perfect fit. Okay. That's called the best fit. So the best fit searches all the entire list, and choose the smallest hole that's large enough to accommodate the request. Okay. And the last actual search is called the worst fit. Worst fit takes the opposite approach from the best fit. So that means worst fit are going to also search the entire memory location and find all the holes that the fit that's actually that can fit the program. But the worst fit may you would put the program into the largest hole. Okay. It will always choose the largest available hole for the request. Now, let's actually take a look at each of the space management. Which one is the best one? Or which one is better than the others? Do you have any idea?
Best fit just kind of seems like the most space efficient,
Best fit.
so that it doesn't avoid putting a smaller program in a larger hole.
Okay. Yeah. Actually, from memory management perspective, best fit seems to be the best approach. Because if you have a couple of actual program and you put some of the programs are big and some of the program is small. Once you actually, if you have two programs, in this case, okay, if I have two programs, one big, the other one is small, okay. So suppose this program actually comes first and this program comes later. So if I use the best fit, basically I'm going to put this program over here, right? And then when program 2 is coming, and then search all the hole, and that the program 2 I can fit into that hole. Now, if I use the worst fit, okay, now the worst fit basically when this program 1 is coming, and I find out, okay, these 3 holes can fit the can fit that program, but worst fit gonna actually choose the largest one, so I'm gonna put this one here. Okay, and then when P2 is coming, and I search all the hole, and none of these holes gonna be big enough for P2. So if I use best fit, then I can accommodate both. If P1 is coming, P2 is actually follow the P1, and I can put the P1 in this here and the P2 in here, right? P1 here, P2 here. But if I use worst fit, then I actually put the P1, which is relatively small program, into a larger hole. So I actually shrink the largest hole. So when P2 is coming and there's no holes that are large enough to fit P2. So in this program, so sounds like the worst fit is really a bad approach. Okay, best fit is actually the best. Now compare with the first fit. Actually, both best fit and worst fit are going to actually search the entire memory space. So the performance is going to be, it's going to take longer to search the whole memory, right? For the first fit, it might be very efficient because when I search the hole and I immediately find a hole which is large enough for the program. So I put the program in and I stop the search. So I don't have to, go over the whole entire memory space. for the host. So that's why first fit probably is not as efficient, as from memory perspective, it's not really efficient, but the performance is probably better. So I really don't know why people use the worst fit. Okay. However, in theory, best fit is the best in terms of memory management. First fit is the best in terms of the performance. Okay. Now, but the simulation of different strategy basically shows a slightly different story. Has not produced a clear winner. So that means each strategy has its own strong point. But I think worst and the best, definitely worst should be eliminated. I don't know why people use the worst, because in terms of performance, the worst and the best is going to search the entire, the memory space. So the performance are equally bad. But in terms of memory management perspective, worst is actually really not good. So I think I can eliminate the worst. But between the best and the first or next, it's really hard to say which one is better. Depend on your criteria. If you think the performance, the speed is very important, then first fit is probably not bad. And if you think the memory actually arrangement is most important one, then you can use best fit, right? So now I'm not going to spend much time on this one, but this is actually the general result based on statisticals. It's called a memory fragment and the 50% rule. Okay. Now, no, regardless which approach you're going to use, if we use the first fit, best fit, worst fit, and the next fit, eventually you will find out whenever you start allocate the program, okay, here's the rack, here's a hole, here's a hole, and then you will find out when actually you start to run and some programs actually added into memory and some program leave the memory, some program more program added memory and leave more program leave the memory. After for a while, you will enter into some kind of scenario that is called 50% rule. The 50% rule basically says no matter which strategy, memory location allocation strategy you use, eventually the memory that is loaded into the program versus the memory that is not loaded into the program is 2 versus 1. Okay, so 1 is basically the memory that are not used. 2 basically means they are used. Okay, so that basically says you have so the number of holes. What should I say? Okay, so I can say this. Now, if 1/3 of all memory partitions are whole and 2/3 are occupied blocks, okay, so that these are the blocks. This is based on statisticals. So in another word, so if number n represent the number of holes, and the number m represent number of occupied blocks, that means the m are the number of blocks that are currently used by a program. So n is 50% times m. Okay, so that means if m is the number of occupied block is 20, if m is 20, then n is 10. So that's the reason why I gave you 2 versus 1. The block is always doubles the holes. And that's also called 20% rule. So I don't want to spend much time because the result is based on the statisticals. Okay. So they have a detailed analysis in the Zai books. Even the Zai book is not detailed enough. Just gave you some kind of some kind of analysis, but that's a general rule. Is this? I don't think this is good, right? So that means if I purchase a computer and I purchase the computer with like a 32 gigabytes memory space, and you think, oh, 32 gigabyte memory space is big, but then you find out with 50% rule, you only actually used 2/3 of the memory space. So that means it's probably like you only used about 20 gigabytes, and another 10 gigabytes are basically wasted because these are holes. Okay, that's not good, right? So now in order to increase the memory actually utilization to more efficiently use the memory space, then you have a couple of approaches to do that. Okay, so for example, if I have blocks here, blocks here, blocks here, blocks here, and you have 3 holes. Now, if I have one program want to come, and then one thing I can do, one approach is I can use swapping. Okay, I can temporarily remove one of the programs. Say, oh, this program, I can temporarily remove. So there's actually in typical computer system, there's a kind of a mirror of the memory actually structure into the physical one. So I can just say, okay, I can temporarily remove this program and put the program back into the hard disk. Okay, so I free up that space. Okay, I free up that space. And then I can actually create the hole, which is big enough for this program. So I fit the program in there. Okay, so then I execute the program, and hopefully, once I completed this program, and then I can remove the program, and then I can move this program back. Okay, because when I actually swap the program, the swap is temporary because that program was in the computer memory, so no one knows whether this program will be executed again. But sometimes if I find out, oh, okay, this program is not used for quite a long time, so let's just temporarily remove the program and put it in hard disk and load a new program in there. Hopefully that once the new program finishes, I can somehow put the program back. Okay, so that's called swapping. Now this another approach is called memory compaction. You probably understand what this mean, right? So the other approach, is this is not good, right? So if I have here, this is not good. I have a hole here, I have a hole here, 3 holes. Now, can I just move each of the program towards one direction? Okay, so I can say, First program is here. The second program I can move close to here. And the third program close to here. And another program close to here. So I just actually move all the program, which is scattered all over the memory location, towards one direction. So that way I can create a big bubble. So this is a big hole. So I can accommodate more programs. Because these are holes. Even though I add all the holes together, it's still a big memory space. But these are not usable space because each hole is small enough. I cannot accommodate a program. Okay. But if I compact this program towards one direction, I can actually free up the space so I can create a usable space here. Okay. This is a very similar approach, just like your hard disk space. In Microsoft, there's a one feature. It's called a fragmentation, right? Or defragmentation. I'm sorry. What does defragmentation do? Because when I actually store the data into the hard disk and then delete the data, store another data, delete another data, and then the hard disk is gonna create the same kind of phenomena, just like this memory distribution, right? So the defragmentation is just doing the hard disk compaction, just move all the files towards one direction, so I can actually make a big hole. Okay, that's another approach. Okay, I think I'm pretty much done with this, and so after this, I'm gonna actually next time we're gonna talk about a new topic which is called paging. So far, when we do the memory management, we assume that all the program can be loaded into the same memory location, into the consecutive memory location. If the program is big, I have to find a big hole in the memory to accommodate this one. Now, the paging actually solved that problem because the paging doesn't have to, using paging, I don't have to load a big program into the same memory location. I can load a piece of the program into one memory location, load another piece in another memory location. So I can actually load the program into a different memory location. So that's this way you can actually utilize the memory more efficiently. Okay, that's something we're going to talk about next time. Okay, I think that's pretty much all. Any questions? So I'm going to post the assignment for the memory management, but you can start the exercises for the first couple of sections, but you can still leave some of the sections we haven't covered yet. Or if you want, you can start to do the exercises. Okay, you can start to do the exercise. You can do the exercises anyway, and once I actually set up the due date, and whatever you have done in the Zybook exercises, it will be counted. So you can start to do the exercises right now for the chapter 6, the memory management. Okay.
Have a good weekend, Professor.
Have a good weekend.
Have a nice day, Professor.